what we looked at last week with imperfections, they also actually influence a number of properties. And one of the properties that we looked at, was that last week or this week? One of the properties we looked at was the electrical properties of materials. So we found that imperfections actually increase resistance in materials. Okay. So there are a number of imperfections that we're going to look at just briefly, then we'll move on to another topic. So most of these, a lot of these imperfections happen actually at the solidification state. This is when when casting is happening. Okay, so when we are extracting these metals, okay, from the ores, and as we are cooling them or solidifying, when that process is happening, usually that's where a lot of defects happen. Okay, so usually when solidification, there's where we have those, as the temperatures are dropping of that molten metal, for example, let's look at metals. As solidification is happening, first will happen in certain areas, okay, in the spotted areas there. That's where you have atoms solidifying and joining together, okay. So an atom will solidify, join together, and they begin to clump in small clusters like that. So be clumping one to the other. So this is what we call the nuclei form, okay? So nuclei begin to form. So this is called a nucleus, this is called a nucleus, okay? A small grouping of solidifying atoms. So these nuclei actually grow later to form crystals, okay? As these are expanding, as you can see over time, they begin to look like this, okay? So as more atoms are joining in, okay, the nucleus is growing and growing, okay, till finally the boundaries will meet, okay, to grow to that level, to that size, to this size here, okay, where you have it now joining with the next nucleus, okay. So the borders there are what we call the grain boundaries. So this was initially a liquid, very hot liquid. I'm sure you've seen a lot of, if you don't work in industry, even just on TV, you see people pouring just from when they just extracted these metals, so be pouring them at that level. Someone saying something, Eric? Eric?
Sorry, madam.
Okay, I thought you were saying something. Okay. All right, so they'll be growing until eventually they look like this. Let me just enlarge a bit. Okay, so this is basically how a typical metal looks like under a microscope. This is the grain structure of a typical metal. It will look like this, whether it's aluminum, whether it's copper. It will basically look like this, the grains, the different crystals joining together and forming these boundaries around them. Okay, so boundaries also in a way are an imperfection, okay? Because where you have one boundary joining the other, usually that's where the defects and the fracture, that's where it first happens, okay? So fracture, whether it's under tensile stress or under any other stress or forces, usually it will happen along the boundaries here. That's where fracture begins to happen. So this is known as a polycrystalline material, okay, because it's composed of different crystals joining together. So many crystals forming one piece of a metal, okay, one specimen. So grain boundaries, like we said, I think this we covered partly when we're looking at crystalline structures. These are regions between crystals, and they transition from lattice of one region to that of the other, and they are slightly disordered, as you can see. There's this arrangement, okay, that looks perfectly okay. And then there's that arrangement coming in that direction. Then there's the other arrangements, okay? So there's an angle there, what we call the angle of misalignment. That is the angle at which this one, okay, is joined to the other grain. So that angle is what we call the angle of misalignment. And this is the high angle grain boundary, and this is the small angle grain boundary. As you can see here, the angle is small. So the misalignment is not so much compared to this one. Okay, so low density in grain boundaries, high mobility, high diffusivity, and high chemical reactivity, all these usually happen where? In the grain boundaries. Okay, so even an atom of another metal will usually find space here and come and fuse itself along this boundary. That's what usually happens. or another metal altogether will come and form right in this boundary. Someone can't see my screen. Can anyone else see my screen? Is there anyone who can see my screen?
It's visible, madam.
It's visible. Okay, maybe I'll just ask the person who can't see Moses, please just log out and log in again. You should be able to see my screen now after you log in, after you log back in. Okay, we move to the next slide. So there's no such thing as a perfect crystal. Okay, there's always got some defects here or there, or imperfections as we call them. Okay, so there are a number of properties actually that are enhanced, okay, not just the negative side any of imperfections. There's also a positive side actually that comes with imperfections of materials that we also take advantage of. Alloying, for example. Okay, alloying is when you have atoms belonging to another material, isn't it? Joining with atoms of another material. So we know that with some metals, when you alloy them, you actually enhance certain properties. Okay, that may not be found in those individual metals, but when they come together, they form this super metal. Okay, that has these enhanced properties that we are in need of for a particular area or project. So these are some of the imperfections that we're going to look at. There's vacancy, what is known as point defects, line defects, and area defects. So point defect is the vacancy atoms, interstitial atoms, and substitutional atoms. Then there's the dislocations and the grain boundaries. We're going to look at them one by one. Okay, we start. So under point defects, we say there's the what? The self, interstitial, and the substitutional and the vacancy. Okay, so now we're going to look at how they look like. So if this is an arrangement of a metal. Remember what we looked at when we looked at metallic bonding? We say that metals are usually in an orderly manner. When we look at crystalline arrangements compared to amorphous is haphazard kind of arrangement, but with the crystalline arrangements, you find that atoms are actually arranged in an orderly manner. Okay, except of course, it's not always perfect. There's always some imperfections here and there, and these imperfections have names. So the simplest form of a defect is a vacancy. Okay, so you see what happened here. You have a normal, proper arrangement of atoms, arrangements of atoms coming on well, but except here, there seems to be a vacancy. Okay, there's an atom that's supposed to be here. There's a space for one atom and it's not there. So if you look closely to the left, let me just increase. So when you look closely to the left, what do you see? There's an atom hiding under those other atoms. Okay, it squeezed itself somewhere in between here. Okay, so this, where there's a void, okay, or where an atom should have been, that is what is known as a vacancy. Arising due to an atom missing, a missing atom in this place. And where you have an atom coming and squeezing itself where it's not supposed to be, there's a pattern here as you can see, and then there's this atom here hiding just under. This is called a self-interstitial defect. So for an exam, usually exam question will come this way, asking you to draw or illustrate how a vacancy defect looks like and how self-interstitial vacancy looks like. A simple question I expect you to answer. So for this, there's a way that we can, okay, let's look at this. Still under point defects. The presence of these vacancies increases the randomness or the entropy of the crystal. Definitely, it's a lack of order, I would say, isn't it? So the order is disturbed when we have these vacancies in the arrangement of the crystal. So it's basically a lack of order. And since these vacancies are tolerable, the equilibrium number of vacancies, which is NV, that's what we call the equilibrium number of vacancies for a given quantity of material, it depends on and increases with temperature. Okay. So vacancies, what are we told here? Since vacancies are tolerable, the equilibrium number of vacancies increases with temperature. So with the rise in temperature you expect the number of these vacancies. Okay, and there's this particular formula in place there. So if it's an exam question, usually how it will come is you'll be given the formula. Okay, and you just be asked to substitute. So usually nothing is for free, even in an exam. So usually if you find that the examiner gives you the formula to use, usually you need to look here, okay, and look at the units, okay, for the data that has been given. So usually if it's I'll hint you that one. Usually if you have the formula there, it means that somewhere, maybe the temperature has been given in degrees Celsius, and you see the formula requires that your temperature should be in Kelvin. So the examiner will deliberately put temperature in degrees Celsius. Okay, so it's up to you to know. Okay, if you've read this before and you've gone through this material, you should realize that temperature here is in Kelvin, for example. K is a constant. And Q is the energy required for formation of vacancy. So all these usually will be given in the question, but it's up to you to convert. So how do we convert Kelvin, degrees Celsius to Kelvin? We add degrees Celsius to those given degrees Celsius, we add 273 in order for us to get Kelvin. Okay. So for most metals, the fraction of vacancy is NV over N, just below melting temperature is 10 to the power negative 4. That's usually the fraction of the vacancies. Okay. And going back to the next slide. For self-interstitial, I think we already looked at it from that other diagram. So when it left here, it obviously it had to go somewhere, isn't it? So it went where it's not supposed to be and went and squeezed itself here. That's basically what interstitial is. Okay, so questions will come also where you'll be asked to calculate the number of vacancies at a given temperature. So there's an example here. It says calculate the number of vacancies per cubic meter for copper at 1000 degrees Celsius. The energy for vacancy formation, you're given that one. The atom weight is given. And the density. So weight and density for copper is given and you're asked to calculate. Okay, so that's a formula to go. Just basically applying the same formula here. You put in Avogadro's constant, you put in the weight, the density there, and the weights, the atomic weight here of copper, which is 63.5 grams per mole. And you find your answer. I think it's not that complicated. You can even go through in your own time. Okay. So what about impurities? Do they exist in solids? So of course, impurities exist. In fact, there's no atom there's no metal that appears in its purest form of 100%. There are always foreign atoms, or what we call impurities. They'll always be found. Those who work in the mining sector will tell you, even just copper extraction, no matter how much you purify it, you can only purify it to 99.999%. I don't know if it's 4 nines after the decimal or 3. I think it's 4. That's the highest purity you can attain. Okay. But even at that 99.999% purity, the order of 10 to the power 22 or 10 to the power 23 impurity atoms would be present in 1 cubic meter. So imagine in 1 cubic meter of that particular material that has this level of impurity, it will have this level of impurity atoms. Can you imagine? 10 to the power 22, that's how many? That's in trillions, isn't it? That's how many impurity atoms will be present even at this level. So now you can imagine if it's at a level of 78% purity, much higher than this, much higher than this. Okay, so this explains why we have alloys in which impurity atoms have been added intentionally in order to impart specific characteristics of the material. So we'll look at that in our next topic. Adding impurity atoms to metals results in solid solution and or a new second phase. So that's what's supposed to cover under phase diagram. So coming to a solid solution, what do we understand by a solid solution? Eric, have you ever heard of a solid solution? Or we covered it with you, I'm not even sure anymore. Brian, Jolwe, Hatu, Mwewa, maybe anyone. In your own words, how do you understand what a solid solution means? Okay, let's start from the top, from the bottom. What's a solute? Or give an example of a solute.
Madam, a solute is a substance that is able to dissolve in a solvent.
Okay. All right, give me an example of a solute.
Salt, sugar.
Okay. All right. Can a metal be a solute? Can a metal be a solute? Yes, it can. Why not? Okay.
Dissolve, madam, it means it can be solid.
Yes. All right. So give me an example of a solvent.
Water.
Water, isn't it? What is known as a universal solvent, because just about so many solids can dissolve in water. All right. So now when let's talk about Zigolo. You make zig, those were in boarding schools. You understand the zig concept very well. You get your sugar and your water and you mix them, isn't it, to make a sugar solution or a glucose solution. Then you get that cup of glucose that you made and put it in the deep freezer. In what state of matter will that water be after like 2 hours?
Solid.
It will be a solid,
It will solidify.
So can we say it's a solid solution? Huh? Yes, it's a solid solution, isn't it? It's a solution that's solidified. Same concept here. Let's go to copper. Copper in its molten state, isn't it? So you've gotten your 99.99% copper. Just imagine you're at KCM, and they're pouring it in those barrels. It's hot, it's red hot, and it's in molten state, it's in liquid form. So you pour that copper and then you get zinc also in liquid form. A certain quantity, isn't it? Such that maybe it would be like 5% zinc and 95% copper. That's a solution you make, isn't it? Let's say 95% copper and 5% zinc. Both hot, both in molten state. You can even mix them with a thing. What do you call that? Industrial mixer. So now, what happens now when you get that copper and let it naturally cool? As the temperature is dropping, what's happening? It's moving from which state of matter to which state?
It moves from liquid to solid.
Yeah, so it will move from liquid. It will even have an intermediate state, which is known as a molten state, isn't it? So it will be liquid, then it will come to a molten state, then it will solidify. So when it solidifies, that is what is known as a solid solution. Okay, initially it's a solution of copper and zinc. Then once it has solidified, it's what we call a solid solution. Okay, so we move on. We move on. Impurity defects are found in solid solutions and are of two types. You have the substitutional solution and the interstitial solution. In the substitutional solution, impurity atoms replace or substitute host atoms. Okay, so now there's a substitutional one that has come in. We looked at the vacancy initially and the interstitial. So vacancy was where there's a missing atom. Interstitial is where that missing atom went to where it's not supposed to be, isn't it? It squeezed itself somewhere. Then for substitutional defects, or in a substitutional solution, that's where you have the impurity atoms replacing or substituting the host atoms. Okay, so you have your copper there. How is the zinc going to mix with the copper? So it means that the zinc atoms are going to go in the solid structure. In the crystal structure as the solidification is happening, they are kicking out the what? Some of the copper atoms, okay, and sitting in that place, forming that alloy. In interstitial solution, impurity atoms fill the voids or interstices, as they are called, among host atoms. So what it means is that these interstitial solution, what do they, in the impurity atoms in an interstitial solution, what happens is that these impurity atoms will come and fill those voids. Remember we said that copper, even at 99.999%, it still has like 10 to the power 22 or 10 to the power 23 impurity atoms in it. Okay, it means that they came and settled in those voids, or they in the either in the voids or the interstices among those host atoms. I think there's an example here. There's a photo to show that. So you have, for example, let's say these blue atoms are copper. Okay. Okay, then we have the zinc one coming in. So you have your copper atoms nicely arranged. Okay. Then you pour in zinc. Zinc is going to go and settle where? The atoms need to squeeze themselves in the structure somewhere. So they'll find these vacancies and they'll come and sit there, substitute. Okay. Then there can also be another atom. Let's say you put in chrome or another metal, for example, that has whose atoms have a smaller, much smaller radius than the copper atom radius. So they'll come, them even this space here is enough for them to settle. Okay, so they'll come and settle in those small spaces there because their atoms are not that big. Okay, so they are small enough to even settle in the small spaces between the atoms. Not even really, they don't even really need this whole big radius like the substitutional impurity atom here. So they'll settle there, settle there, settle there, settle there. So this is also another form of interstitial, apart from the other one that just went to the huge atom and just came and sat here behind. No, even this one is regarded as interstitial. Okay, so the degree to which a solvent dissolves a solute depends on the following factors. So these are the, please take note of this. The factors on which a solvent dissolves a solute. So atomic size factor. So the size of the atom matters. Difference in atomic radii of the two atoms must be less than plus minus 15%. Okay. So you saw on the other one, isn't it? So the difference has to be like this. And the crystal structure for both atoms must be the same. So what does this mean? If FCC, then the other one must be FCC. Okay. If it's BCC, if the host atoms are BCC, it means that the impurity atoms will be BCC also structured. Electronegativity, one atom more electronegative, the other more electropositive. So this is intermetallic compound instead of a substitutional solid solution. So it means that the difference in electronegativity must be there. They shouldn't have the same level of electronegativity, but the electronegativity must be different. Atomic size factor, here we say the atomic radii of the two atoms must be, the difference in the atomic radii must be less than 15%. In terms of valencies also, more tendency to dissolve in another when one has a higher valency than the other. Okay. Give an example. Let's come to valencies. We already covered this atom. What valencies do you know for which atom? What's a valency for magnesium? We remember. No one remembers. Anyway, so if you have a 2 and a 1 and whatever, so meaning the tendency to dissolve in another when one has a higher valency than the other. Those are the factors on which these solid solutions depend on. So an example of a solid solution is copper and nickel. Okay, this is an example of a substitutional solid solution. This is copper and nickel, because the atomic radii for copper and nickel are 0.128 and 0.125. As you see, they're less than 15%. So meaning their sizes are quite very similar, almost the same size. Okay, so that's why it's easy for that copper, that nickel atom to substitute a copper nickel. Okay, because it will fit almost perfectly in that place. Why? Because the their atom sizes are the same, or the atomic radii are actually almost the same. Okay, so it's easy for this size to come and fit in a space for this one. They both have FCC structure, crystal structure, face-centered cubic structure, and their electronegativities are 1.9 and 1.8. So one is more electropositive than the other. So this one is more electropositive than 1.9. The most common valencies are +1 for copper and +2 for nickel. As you can see, we say that for the valencies, one must be higher than the other. So copper usually has this valency. Usually it occurs as +1. Okay, and nickel will be +2. So there'll be that difference in valence. Okay, so coming to dislocations or linear defects, we say that virtually all crystalline materials contain dislocations. These dislocations can be introduced during processes such as solidification, during plastic deformation, and as a result of thermal stresses due to rapid cooling. So when you have rapid cooling, how does rapid cooling happen? When you obtain that molten state of a metal, okay, sometimes in industry, you will not wait all day for it to cool under natural temperatures. You won't just be hanging around waiting for it to cool. But sometimes what happens is that it's put in those barrels, okay, or in the molds. Usually it's put in the molds, and sometimes it's placed into those while that metal is still hot and in a molten state. It's placed into a pool of cold water, for example. Okay, just to speed up that cooling process, and that is what is known as rapid cooling. Equilibrium cooling is where you naturally just let it sit, okay, and just let those cooling processes happen naturally. Those forces on it and the cooling processes happen on it naturally. That is known as equilibrium. But where you speed up, you try to speed up, where you aid the cooling process, that's now rapid cooling. And so during that cooling process, rapid cooling process, some dislocations tend to come up. So they're found in metals, they're also in ceramics, and also polymers can have defects. The dislocations can be observed in crystalline materials using an electron microscope. So we have a picture here where we can see some of these defects under a microscope, how they look like. Okay, so there's that defect there coming up. There are these boundaries. You see that they're not, there's the angle there that was trying to draw, just basically to depict some of these. You can see there's this arrangement of electrons and there's some bending there happening, okay? Or some dislocation of some sort there where they have the white there, the whiteness happening there, that to show that there's no uniformity in the arrangement of atoms, so meaning there's a dislocation there, a kind of line defect. Okay, as you can see, you can actually draw a line across it. Same as this one here. So how does this happen? Or what is it rather? It's a linear or one-dimensional defect in which some of the atoms are misaligned. So there are 3 types. This is also an exam question. There are 3 types. There's the edge dislocation. This is trying to call me, I don't know why. There's the edge dislocation, and there's what is known as the screw dislocation and the mixed dislocation. So edge dislocation is a linear defect that centers around a line that is defined along the end of the extra half of the plane. So it kind of forms this T. Okay, it's known as the edge dislocation. It kind of forms a T where you have these arrangements. Okay, so you have this line, okay, this line of atoms. You have the second line of atoms, the third line. You have this one complete to the end, this one complete up to the end, this one, yes. Then there's this one here that just hangs in the middle. As you can see, it's suspended somewhere here. It does not follow all the way through to the other end, to the other edge. Okay, so it forms what is known as a T. Okay, it usually happens at the edge. So you have this forming up. So you have this line not being complete, and it kind of forms a T there. turned upside down. That is known as the edge dislocation. Okay, so what happens usually is when stresses are applied to these, isn't it? We say that, so plastic deformation, when the material is undergoing plastic deformation, that's when these dislocations begin to happen. In short, some force of some sort has to happen on it. So an example is this one. There's this type here. As you can see, there's this line here, this one coming down, that one, then there's this suspended one. So the T kind of formed here. So in this one, the atoms are displaced, causing the dislocation to move one Berger's vector on the slip direction. So this is known as the Berger's vector.